So we were in the module 1 of the engineering statistics and linear algebra. We tried to solve till 72 in the last class, and now we are trying to solve the question number 73. That is, given the random variable x is uniformly distributed between plus r minus 2, the function gx is given as y equal to gx equal to x squared, x greater than or equal to 0, minus x squared, x less than 0. What are the CDF and PDF for y? Right? So given this, we should be able to find the inverse, G inverse of y, x equal to G inverse of y. We should be able to find out from this. So let us see the solution there. fxx is within the range, minus 2 to plus 2. That's what is mentioned there, if I'm right. Right? Plus r minus 2 will give minus 2 to plus 2. So therefore, it is between minus 2 to plus 2. Because it is between minus 2 to plus 2, the total range is 4. So therefore, for the area to remain 1, under the PDF, we should have this as 1 by 4. You should have this as 1 by 4. So if you integrate this, then you'll get x by 4 as within this, and 0 for less than minus 2. This is again a mistake over here. This is 0 for less than minus 2 and 1 for greater than, plus 2. Greater than plus 2. Less than minus 2 will be 0 for the CDF, and greater than plus 2 will be equal to 1. That is the full probability, total probability, so to say. So Fyy will be P of y less than y, and this is nothing but in terms of x will be, because we have these two quantities, y is equal to gx equal to x squared by and minus x squared for x greater than 0 and for x less than 0, right? For negative values of x here and positive values of x here. So if you take that, then we'll get it as minus of root of y less than x less than or equal to y. Okay, so this will be the range over there, and the graph for that will be something like this. The graph for that will be something for whatever we have written here. The graph will be something like this. That is, y takes the value of minus x square for x less than 0. So if x is negative also, x square will become positive, but y will be negative. Therefore, we will get it in the quadrant, which is third over here. X is negative, y is also negative. That's why we are in the third quadrant. For x greater than 0, x is positive and x square is also positive. That is, y is also positive. We are in the first quadrant. That's why the graph for this I have drawn like this, right? So you can have for y greater than 0 this range, and for y less than 0 this range. You will have minus y in the root, minus y in the root. Okay, so both the quantities for y greater than 0 will be this, for y less than 0 will be with a minus sign with y there. Less than 0 means it will become, negative. So negative root you can't have, so you take the positive of that, and hence you get this quantity. Okay. So if you take the, this one, you try to solve this, then you will get the values as, root of y by 4 minus of root of y by 4 as the values there, because at the end, the value of x is nothing but, we have got here x by 4. So this x is that, root y minus root y, whatever it is. So wherever that quantity is there, it will just get divided by 4. So if you just get divided by 4, you will get this quantity as root of y by 4 minus of minus root of y by 4, y greater than or equal to 0. And similarly here, minus of root of minus y by 4 minus of minus root of minus y by 4. This is coming because you have two different, limits, right? So if you add them up, minus of minus will become plus, minus of minus will become again plus, and hence we will get this quantity as root of y by 2 and minus of root y by 2. Now if you want to find the yy, which is the PDF, you need to differentiate that above one, this one over here. So if you differentiate that, then you'll get fx1 by, you need not write this really speaking, you can just differentiate that and write it over here as 1 by 4 1 by 2 root y minus 1 by 4 1 by minus 2 root y, and these two will get added up. That will become 1 by 4 root of y, and again you can write this, and these two will get added up and you'll get 1 by 4 root of y for y less than 0. Okay, this is how we can try to solve this. Then let us solve 74 also. So 74 is this, that is the random variable x is Gaussian and mu x is equal to 0, mu sigma x equal to 1. The random variable y is obtained from x using y equal to 10x cube. This is the equation. So x will be, y by 10, x cube will be y by 10, x will be cubed root of y by 10, right? So with respect to that, we can try to find out the value which is fy of 0.1298. So mu x is given, sigma x is given, Gaussian random variable is considered, y is equal to 10x cube, so x will be equal to cube the root of y by 10. Fyy will be equal to p of y less than or equal to y, and that will turn out to be x less than or equal to cube the root of y by 10, which should be written from here, right? And if you try to write there the value of y, we want to find fy of 0.1298. So therefore the value of y is this. So here y should be substituted with respect to that, 0.1298 by 10, and this quantity will be 0.1298 by 10. Cubed root of that will be 0.235. So from that you can from the table, okay, this value you can read it 0.235, and that turns out to be this, and that can be read something like this. You go back to the table here. Yes, 0.235, 0.2 is there here, 3 is there here, and 5 means exactly in between. In between means midway between these two, average of these two, okay, average of these two. Or you can take difference between this 48 and this 10 will be 38, divided by 2 will be 19. 19 should be added to the 10 over here, so therefore you'll get 5929, 5929, and that is the value which I have written there. Okay, that is the value which is written here, which is 0.945929. Okay, similarly, let us go for solving the 77. So 77 is given the transformation y equal to gx, that will convert the random variable x, which is uniformly distributed between 0 and 1, into the Laplace random variable y. Okay, so see the appendix A for the description of the Laplace random variable. Okay, so we are given the transformation here, and we need to convert it into the what you call x is given and y we need to convert, and y is in the Laplace random variable, right? Then whereas x is the uniformly distributed case, so what will it correspond to? The Laplace random variable is what we need to solve. So 77 is, we are given with fxx equal to 1 0, which is within the uniform random variable. This is 0 to 1, that is what is given here, right? 0 to 1, and once that is 0 to 1, this will become automatically 1 because area should be 1. 0 to 1, length will become 1, so height will be 1, so that area under the PDF curve is equal to 1. So if you integrate this, you will get again this. Again, there's a mistake here, that is for x less than 0 it is 0, for x greater than 1 it is 1. However, if you differentiate the whether 0 or 1, you'll always get 0, and this will become 1. Okay, if you differentiate this, you'll get this. If you integrate this, you'll get this. So there is a mistake in this, otherwise it should be 0 for x less than 0 and 1 for x greater than 1. Okay, so now we need to find fyy is equal to fxx. Fyy is from the Laplace what you call transformation, which we would have taken in the appendix A. Let us see whether we have that. Okay. Yes, appendix A is here. Okay. So here Laplace Gaussian. Okay. Okay, this is the one which we are considering over here. Is it that which we have taken? Just check it out. No. So am I doing that only or something else? 77. What is 77? Laplace. But Laplace is not that. So am I doing what is that rally which is there here? 70. Oh, sorry. Cauchy. 77 is, sorry, Cauchy is random variable, not 78 is Laplace. So let us see Cauchy's. Yes. So it is Cauchy's random variable which you are considering. By mistake, I said Laplace random variable, that is 78, but in 77 we have the Cauchy's random variable. So this is the equation which I have written over here. 1 by pi tan inverse of y by a plus half is equal to x. So this half you can take this side, so it will become x minus half. Then this 1 by pi you can take this side, it will become pi. Okay, this tan inverse you can take this side, it will become tan, and this a you will have to take there, so it will become a tan of x minus half pi. So this is the final solution corresponding to this. Okay. Similarly, if say the next one Laplace is given, we need to consider that Laplace equation and try to solve this and get it in terms of y. If it is Rayleigh, you can what you call find from appendix what is Rayleigh and substitute that and try to get it. Okay. So for Laplace, you need to consider both these for x greater than 0 this one, and for x less than 0 this one, and try to solve that and get the value of y in those two cases for x greater than 0 and x less than 0. Similarly, you can consider for Rayleigh. Rayleigh might be after that is here. So again, it is for greater than 0 it is this, and for less than 0 it is this. You can write this and try to solve it for that and get the equation. Okay, so that finishes the part 1 rather, but still we are left with quite a number of solutions there. So let us try to see some of them. Okay, 58 is the question which we tried to see, we didn't solve it. So the solution is something like this. Use the characteristic function of the Laplace random variable found in the appendix A to find the first two moments about the origin E of x and E of x square with these results, and find the variance sigma x square also. Okay, so we are given the for the Laplace random variable, I think here we have the Laplace random variable, the phi there. Yes, phi is this, b squared by omega squared plus b squared is the phi there, and that is written as b squared plus omega squared. That is written as plus omega squared is written as minus of j omega square. So j omega square, I'll just So we were discussing this b squared by b squared minus j omega squared. So if you differentiate this with respect to j omega, this quantity, then you will get this as, you know, what you call, this is like, this is a constant, however. So you'll get 2b squared j omega, which is the, differential of internal derivative of this. So you'll have to get b squared divided by b squared minus j omega square whole square, okay, whole square multiplied by the internal derivative of the quantity, which is b squared minus j omega squared, and that will turn out to be the quantity which is, uh, j omega. That quantity will be j omega. So similarly, you take the differentiation of this with respect to j omega once more, you will get this quantity. Then using the equation which is 2.91, the mu x will be the quantity which is, this value, that is differentiation once, with respect to, substitute there omega equal to 0, so you'll get 0 itself. Okay, this quantity at omega equal to 0 will give you the mean. Similarly, e of x square is this quantity at the omega equal to 0, that will be 2 by b square. And then the variance can be found as sigma x squared is equal to e x squared minus mu x squared is equal to 2 by b squared. Okay. Then we have the question number 70, which we didn't solve. Show that the characteristic function for a Gaussian random variable x with a mean of mu x and a variance of sigma x is this quantity. So for that, you need to take again the, for the Gaussian random variable, this, phi x j omega will be equal to e to the power of minus omega squared by 2. This is the standard format, and that can be written as j omega squared by 2. And if we try to write y equal to sigma y x plus, mu y, this is the standard equation for the mean, which we can do the transformation, and then we can just write it over here as phi of y j omega will just correspond to, you need to substitute, the quantity there, that will just become e to the power of j omega mu x multiplied by e to the power minus sigma squared omega squared by 2, and that will be nothing but exponential of this quantity. Okay, so you just need to use this relationship over here to put it in the equation 2.89, okay, in the chapter 2, okay, 2.89 in the chapter 2. Uh, 2.89 is much below down. 2.89 is here. Yes, this is 2.89. So if you substitute it over here, that is j omega ax plus b, whatever quantity which you have written in place of a, I think it is sigma x, and in place of b, it is mu x. If you substitute that, you'll get this whole format like this. So that it's as simple as that. Okay. So that is question number 70. Then we have 81. 81 is the random variable x is uniformly distributed between -2 and +3. Y is related to x using the plot shown in the figure 2.16. Find the CDF and the PDF for the random variable y. So for that, we need to consider the figure which is over here. So here you can see that it is taking the value of y is either -1 or +2. So when y is -1, only two values for y, -1 and +2. So when it is -1, what is the value which we have here? And that turns out to be 40, and when y is equal to 2, it turns out to be point, 60. Okay, so minus 1 will be between minus x between -2 to 0. Okay, uh, so total range from -2 to 3 is 5, right? From -2 to 0 it is 2. So that 2 by 5 will be 0.4. That is how it is got. And positive values of x will give you 0 to 3, 0 to 3, and the total range is 5. So 3 by 5 will give zero point 0.6 for the value of y equal to +2. So +2 will be for x positive values, -1 is for x negative values. Negative values are 40%, positive values are 60%. Therefore we have the probability like this. So fyy is 0.40 uy plus 1 plus 0.60 uy minus 2. So y plus 1 is because y is -1 for this, and y minus 2 because y is equal to +2 for this. I think you understand, what you call, you might have done the same thing in the signals and systems there. Okay, now this is nothing but it is nothing but fx, capital Fx, when fy, capital Fy, when y is equal to 2. This is capital Fy when y is equal to -1, and that will give you u of y plus 1 here and u of y minus 2 here. If you differentiate this, u becomes del. Unit step will become unit impulse. Unit step will become unit impulse. Similarly, 80 and the 82 can be solved in the same way. So it's very simple over here. Then we come to the 83. The random variable x is the Gaussian with an arbitrary mean mu x and variance sigma x square. The random variable y is obtained from x using y equal to of x. The random variable y is called log normal random variable. Show that the PDF for the log normal random variable is this quantity. Okay, so we are given y is equal to e to the power of x. So x will be log of y. So fyy will be p of y less than or equal to y. So in place of this, we need to write x, which is less than this log of y, and this is nothing but fx of log of y. And this is the CDF, and the PDF will be the differentiation of the CDF over here, and that is the PDF of the original one, then the internal derivative of ln y, that is 1 by y, right? And this is nothing but again the log normal what you call function of the PDF, which we need to consider, and that is what 1 by y is taken out here. Rest is the log normal combination with sigma x out of 2 pi exponential of this whole thing. Okay. Similarly, 84, given that the PDF for the log normal random variable is this, find the CDF for the log normal random variable in terms of the normalized Gaussian random variable phi z. So we are given this. So phi fyy is integral of whatever is given to us over here, and that turns out to be this quantity over here. And having written that, you just need to substitute that is equal to ln minus mu x dx, and this quantity is what is z, and hence we will get this quantity. But y will be, if this is equal to z, then what will be the value of y over here, and that will turn out to be this quantity itself, ln u minus mu x by sigma x. Okay, and that, if you see over here, is the limit which which we are considering here. In place of y, we have this quantity, and therefore in place of this y, we should have this total quantity ln of y minus mu x by sigma x. Okay, this is how we can solve the 84. 85 is A similar one, given that the PDF for a log normal random variable is this quantity, use the change of variables of this quantity and integration technique for completing the square to show that the nth ordered movements about the version are this thing. Okay, so again we are taking the this quantity e to the power of yn over here will be equal to this is log normal. By using the log normal equation, which is might be there in the appendix A. Okay, this is the log normal equation, and that gives you the expression like this for CDF and PDF. This is the expression. We can do that and then see what it can be done. So in the solution, if we need to write this over here and then use the change of variable z equal to ln y minus mu x sigma x, then the quantity will get reduced to this one. So completing the square, we'll get z minus n sigma x squared is equal to z square minus 2n sigma x z plus n square sigma x squared. Then you can try to substitute that over here and you can take out the quantities correspondingly, and then that turns out to be this. So see this solution in a little more detail because time is not there. I'm going a little fast. Okay. Similarly, you can go through this solution also. Okay, given that the following are nth ordered movements from the version for the random variable, you can try to solve this. This can be again considered an exercise for you. Try to solve this, and then we will see the rest of the things in the next lecture, which will be tomorrow. Tomorrow we will take approximately one session at the same time, might be 10 o'clock or preferably 9:30 itself. 9:30 we'll have. Tomorrow we'll have class at 9:30 Sunday and close the numericals which are there over here, right? Okay, I'll stop the recording.